Welcome to CMake Training Session 2, where we're going to talk about some more advanced CMake concepts that is hopefully going to get you a little more set up to make real CMake build systems.
Why the fuck?
So we're going to start
Hello?
with a short history of CMake. And so CMake was originally created in about 2000 by a company called Kitware. So they were contracted to develop a new build system for this bioinformatics system called ITK, and the system they made was called Cross-Platform Make, or CMake. So the goal of this system was to be able to read a build script in a single format, like Makefiles for Linux and Mac, and Visual Studio projects for Windows, and generate Visual Studio projects and Makefiles. So have something like Visual Studio projects or Makefiles, but you'd write a single one for all platforms. It would generate the things that were appropriate for each platform. And it needed the ability to support some pretty complicated configurations like custom commands, third-party libraries, and things that generate their own source files, all sorts of complicated build processes, because this was a pretty complex program that it was being used to build. So the original version of CMake that was produced was pretty different from the one that we use today. It used almost a completely different set of commands. They've been slowly deprecating everything from that kind of original version. Like it didn't really have the notion of properties, which we'll learn about today. It didn't have generator expressions. It was like a caveman version of CMake. But the same original concept was kind of there. And over time, that evolved over about 2 decades into what we have now. One of the big milestones was in 2006. They started using it for the KDE project, like the desktop environment. It was like one of the first huge projects to switch to CMake, and they gave it like rave reviews. So suddenly it became pretty popular in the open source community. They kept releasing it for free, and a bunch of people started switching to it. And finally, in 2014, CMake 3.0 was released, which introduces a lot of the more fancy features that we use in modern build systems. So part one, we're going to be talking about targets and properties, two very important concepts to know about CMake. So what is a target? So a target is anything that CMake can build. It could be an executable, static library, shared library, object library, or a custom target. We'll talk about these gradually, but just know that the entire purpose of a build system, the entire reason it exists, is to create targets. Building targets is the goal of your build system. So every single code file is part of one target or another. If your code file isn't part of a target, it's not going to get compiled. So, and all dependencies between code files, like you might have one target that uses another target. All of those dependencies are always expressed between targets. You don't really have dependencies between files like you might have used with Makefiles. You can only express dependencies between targets. There's some exceptions with custom commands, but we won't talk about that right now. But and when you say we have a dependency on, we mean that if X depends on Y, that means it requires Y to be built before X is. Like maybe Y will have some kind of side effect of building it that X needs. CMake will always do it that way. Most common side effect, of course, would be creating a library that something needs to link to. So yeah, dependencies are, and so if you have a like executable or library that uses other libraries, it'll automatically create dependencies for that. So it'll know to build them in the right order. So first of all, executable targets. Everyone knows what I mean by that, right? Right? So executable is just a program that can be run. Like on Windows, it's a .exe. On a Mac or Linux, it has no suffix. And on microcontrollers, that would be like the entire program that gets downloaded to the microcontroller is an executable or executable. Everyone tells me I say it wrong. I know. So these are created by the CMake function add executable. So static library targets, are created by add library with the static keyword. So what this does, and we'll talk about this a little more next time, but it just creates a library that's just full of code files, and that code can be linked into executables or other libraries. Static libraries are very straightforward. They're basically just take a bunch of code, put it in the library, don't do anything extra. So, and you can take these static libraries and integrate them into other things. They aren't really very usable by themselves, but you kind of need to know. The downside of it being very simple is that you need to know what the library is in order to use it properly. We'll cover a little more about why that is next time, but just know that they're kind of the simple one. They're usually used like inside a specific build system, not so much used for something that gets installed. And these have the .lib suffix on Windows and .a on most other systems. So if you see a .a library, know that that's a static library. Next, we're going to have object libraries. These are created by add library with the object keyword. So these create object library, which is basically just you take code, right? Remember last time you take code, you compile it into objects. Those objects are all good, right? And then CMake just lets those objects sit there. And then later you can use if you reference the object library in something else, it will take those objects and build them into the other thing where you reference the object library. So conceptually, they're very similar to static libraries, except it's a bunch of files on the disk instead of a single library. There's a couple of differences, but they're pretty advanced, and you likely won't have to deal with that. Most common use of object libraries is like if you have a certain thing that needs to get built into multiple different like libraries or executables, you can build the common object as an object library and then just link those in instead of building them like 5 times for 5 different things. They're mainly used to improve performance in large builds. You move some stuff into an object library. So what you don't do through functions in CMake, you do through properties. So these properties determine the specific details of how CMake builds a target, such as compile flags and link libraries. Like we talked about that last time a little bit, right? How we have compile flags, which basically tell the compiler how to build your code. Might be like add a certain directory to the include path, like build this code in a certain way, add debugging information. Those types of things are usually controlled by properties in CMake. So properties are one of the most core concepts of CMake, and it's really important to know how they work. So CMake generally attaches properties to specific things. So you can have global properties that are effective for the entire project, directory properties. So these affect the current directory and all subdirectories, and they're kind of cascaded. So like if the current value of a directory property includes all of the directories above you. Target properties are bound to a specific target and will be used everywhere that target is used. Finally, source properties are bound to a specific source file and will be applied to that source file everywhere that it's used, even across multiple targets. If you go to that Git repository, you should be able to open the slides I'm using. This link is super helpful. It's also like the first Google search result for CMake properties list. This has all the properties that CMake supports. Believe me, it is a lot. And you will never use about 99% of these. So I'm going to talk today about the ones that you really will use and need to think about. And you can feel free to go to this doc page if ones come up that you haven't used before. So number one use of properties is adding compile flags. So in order to do that, there's pretty much 4 very important properties to know. So the first one is include directories, and that just adds -i directories. It's a list. Here's some directories, add these with -i. Next one is compile definitions. So it's another list. Here's some macros to define these with -d. Now we have compile options. This is another list of like compiler options like -o, -g, that kind of thing. Just means pass these to the compiler. Now, include directories and compile options, these didn't get added as source properties until CMake 3.11, which is a pretty recent version. So like RPL, we use CMake 3.9, so we can't actually use those in our code base because they might not actually work. So it's always good to keep in mind which things were added really recently. So yeah, those were added very recently. Source property compile definitions was added earlier for some reason. I don't really know. So finally, position independent code is a property that says basically whether the code will be built in such a way that it can go into a shared library, which we'll talk about shared libraries a little more later, but basically you have to build your code a specific way or it can't be put into one. So CMake has a couple of different ways you can set properties. Unfortunately, some of the functions that they give you are really weird, and they have like hidden syntax gotchas. Like, oh, can't use this to use a property with a list value. So I always recommend just sticking with the normal set property function. Don't use like set target properties or set source files properties. Just use regular set property, and you can specify which type of property you'd like to set. And then you give the property name, and then you can use a list value. It's very, very verbose, but at least it's consistent. That's my recommendation. So you can also use some properties to configure targets. So a really common one is target property output name. This basically says, make the file on the disk have this name that's built for this target. Now, normally the file is named the same as the target, right? So if you create a target called like foo, then it'll be like foo.exe. But what sometimes you run into issues with that. Like, what if you want to have both foo.exe and libfoo.a built by the same project? Normally, that would require they both be called foo, and CMake doesn't let you have two targets with the same name. So you have to use a property output name to rename that target to something else that's more useful. So then that way you can have the two things be called different things, but they generate output file names that are what you want. Another thing to know about is install rpath. So property install rpath basically says when you run this program, it controls where it looks for the shared libraries that it needs. So it'll search for those folders, try and find things it wants. This is only really relevant on Linux and Mac. We'll talk about that a little more next time. Property sources is also useful because then if you access that property, there's a get property just like set property. So you can use that to view what source files are attached to a target. So like if you want to make complicated logic that like detects if a specific source file is on a target, you can get property sources. You can also set it if you want to add source files later. Finally, property link libraries is important because that determines what libraries are linked into a specific target. And there's nothing more important in CMake than linking libraries to a target. Believe me. So libraries can be linked to a target using the target link libraries function. What this does is it sets that link libraries property. So what linking does, I know we talk about that word a lot in these. What linking does is fundamentally it says, I have this library, right? And I have this executable. I want this executable to be able to reference code in this library by calling it. So that means basically join the two code bases together and take whatever is needed from the library and put it into the executable when it's actually built. There's a couple different ways this happens depending on what type of library it is. Like a static library would actually just get merged completely into the executable code. A shared library, on the other hand, would not be merged. It would just have it would be referenced. So that at runtime, it'll know, just refer to the code in the shared library, but don't actually combine the two. It saves disk space that way. Just reference code without actually combining them together. So dependencies using target link libraries are multi-level. So if you do target link libraries of lib A to lib B and lib B to lib C, then when you build lib C, that'll include both A and B because lib A is a dependency of lib B. So all the dependencies of the link libraries are also aggregated up to the top. A little confusing, maybe, but it's very useful once you're doing things with a lot of libraries. You don't have to worry about the dependencies of your dependencies. So, and the other reason this is useful is linking libraries doesn't just merge the code. In CMake, it will also pull in the interface options of the libraries that are being linked. So interface properties are a CMake concept used to carry dependencies between targets. So many target properties will come in two versions. There's a private version, like compile definitions, and an interface version, like interface compile definitions. So the private version does what it says on the tin. It affects the target it's set on. The interface version, on the other hand, affects every other target that links to this target. So it has no effect on the thing it's set on, but it has an effect on other things that reference the thing it's set on. It's kind of like the public versus private versions of like C++ classes. A little bit, like what other people see versus what we see. So why do we care about interface properties? So consider this situation. So we have like libfoo, right? And foo.h does pound include readline.h. That requires a specific compile flag in order to compile. So now we have like libbar that includes foo.h. So anyone see the problem here when we're writing the build system for libbar? Why would this be a problem? This header needs this specific compile flag to compile, but we include this header from a completely different library that has no knowledge of how libfoo works. See why that might be an issue? Let's see, question. Is there an interface version of include directories, or are all include directories from a target linked to all targets it linked to? Yes, there is interface include directories. We'll talk about that a little bit more in a bit. But yes, most common target properties have an interface and a non-interface version. So anyone see the problem with this? Why is this
I
a
mean,
problem?
is it just that bar doesn't know that it needs to have the that include flag?
Exactly, yeah. Bar doesn't know that it needs to have that include flag. So the solution is to set the interface include directories of foo to include that specific include flag that foo needs to compile. That way, when bar uses foo, it'll pick up that flag automatically without bar having to know anything about how libfoo is built or how it works. So it's used to kind of carry these dependencies and encapsulate flags within a single target in the build system without you having to mess around with it.
So sorry, just to clarify, like that property is associated with foo in the build system. So then when bar looks at foo in the build system, it looks at all the properties foo has.
Specifically the interface properties, yes.
Okay.
Doesn't so yeah, it'll look through the build, it'll look through the properties, but not the interface. It'll look through the interface properties, but not the non-interface properties. It'll pick up all those flags.
So by default, any compile definitions you add to a target, those aren't carried over to other targets unless they're in interface.
Exactly.
Compile definitions. Okay.
So, all right. So now we're going to talk about adding a static library. So this will draw a little bit on what we had from session 1. Does everyone still have their directories they cloned from that? So let's see.
Sorry, what was it? What was it called?
It's called CMake training. Let's see. If you're watching this on YouTube, I'll put the link in the description for where to clone it. So let's see. So everyone should have the CMake training folder and exercises. So you should have. You make sure to pull the do a git pull to update to the latest version because I've added the session 2 stuff in there last night. Everyone got that? Do the hand raise thing if you do have it set up, or let me know if you have trouble. All right, 1 out of 5. I'll give you guys a few minutes. I'll also send a link.
I'm using the CS104 VM. Does anyone know the password for the user?
It's developer. Yeah, that's right. That's right, Jasper. All right, 2 people.
Jamie, what where was the CMake training located in Git? Because I was just lazy and downloaded it and actually
Jasper sent the link in chat. All right, 4 people. Another minute. Let's see. While we're waiting, so how to do this setup is you're going to open up a terminal to your CMake training exercises session 2 folder. Right now, if you're on Windows, you can use a WSL terminal. Otherwise, Linux or Mac, just open a regular terminal. Or you can use MinGW. Let's see, that's not the right terminal. No, I had one set up. Gotcha. I'll make the text size a little bigger. This is pretty small. There we go. Now you should be able to see a little better. Let's see. So I'm in the build directory. Wait, hey. There we go. So make dir build, cd build, CMake, ... All right, so we can see that our build system from last time, rather I imported the solution from last time, loads up, it generates, it does a basic configure, and it gets ready to go. So we can see that this build system is working. However, there are ways we can make it better. So if you look, so this is what our top level CMake list.txt currently looks like. It's not bad, but it could be improved. So the first thing that we're going to do is conceptually moving quadreg, right, should be its own library. It's kind of weird to just have it lumped in with the test code. So what we're going to do is separate that out into its own library. And there's another annoyance with it, which is having to include the quadreg directory here. Like, we shouldn't, the test code shouldn't have to know how to include that directory. It should be grouped with the code itself. So we're going to fix that here too. I bet you can guess how we're going to do it. So let's see. Is there anyone who's having trouble getting the stuff set up? Need any help before I get started?
Jamie, can you just revise exercise 1 again? I don't exactly remember what we did, so it's a bit confusing.
So if you remember, so exercise 1 was we wrote this CMake file right here. So basically what it does is it builds this quadreg program, and it also builds this test suite, and it compiles them. That's all it does. Is there anyone who has questions looking at this code, like doesn't remember how something works? Now's your time to ask.
Well, not about how it works, but is that the same CMake file that's in the solution session 1 exercise 2 folder?
Yes, exactly.
Okay, great. Thank you.
It's that exact one.
Oh, is it already in?
Yeah, I already gave you guys the skeleton code.
Okay, great. Thank you.
You should be able. That's what it. So this is you should be able to compile the skeleton code as it is, and it should work. What we're gonna do is change it and make it better. The first thing that we're gonna do is we're gonna add a new CMake list.txt in the quadreg folder. So get rid of some of this stuff we don't need. So in this quadreg folder, hey, this is out of date. Hey, dude, come on. Can delete. There we go. Let's make a new one. So wait. So I'm gonna save that as CMake list.txt. There we go. So now we have this right there. So that window a little smaller so it's not covering up everything. So what we're gonna do is we're gonna add a new library. You guys, hopefully you guys remember what I'm doing here, right? So what we're gonna do is set. All right. That makes so what this is going to do is it's going to create a new library. Everyone understand what's going on here? So this is using the same set notation that we learned about last time, and now we're using the new add library command to create a new library.
Jamie, do we always need to include the .h file as well, or is one of them enough?
That's a very, very good question. So adding the .h file to this is kind of, so the historic reason was that it didn't matter. As CMake, when it's building C++ or C code, CMake will automatically discard anything that it deems like not code, like .h, or if you added like a .text, you'll just get rid of it. However, if you're writing a build file for CLion, CLion does require the .h's to be added to the source list. So if you want it to show up properly in CLion, you do have to add them. Otherwise, it doesn't matter at all. It's kind of an annoying thing about that, but I can understand why they did it, because otherwise it's hard to tell like what target the .h goes with and how it should be built.
But in our hamster project on GitHub, we don't have the .h's in the CMake, or do we?
I think we do. I think it automatically finds all the .h's.
Okay.
Well, We glob our source files in Hamster, don't we?
Yeah. So I think the glob finds .h's as well.
That's for the core libraries, but when you're linking from the library folder, I don't think so you have the .h. I'm not sure.
You'll have to show me what you're talking about. I'll take a look after.
That's fine. Yeah.
All right. So see, adding a .h is optional. You could delete this line and this code would work the same way. But if you load it into an IDE, you want the .h in there. So can anyone tell me what type of target this is here, moving quad reg? Well, how are we creating it? Yeah, static libraries target, exactly. So that is a static library target. And what this will do is it'll build a static library with .a extension. So now we are going to talk about interface include directories. So this is going to fix this include problem. So what we're going to do is add a call to target include directories. Target include directories, moving quad reg public dot. So this function is shorthand for setting the include directories target property. So, and this keyword determines which properties it will set. If this keyword is private, it will only set target property interface include. If this keyword is private, it will set include directories only. If this keyword is interface, it will set interface directories only. And if it's public, it will set both. It's kind of like a public member variable in C++. Like it'll be publicly visible and privately visible. So what this is, it's shorthand for setting two different properties at the same time. It's a very useful function. Definitely use it. And remember, all paths are always relative to the source directory. So we're saying add the current source directory as an include directory. You could also replace this for reference with CMake current source dir. And that would have the exact same effect, except it would be an absolute path, but it would do the exact same thing. So that's going to add that there. So now what we are going to do is we are going to go back to the upper level CMake list.txt. So what we're going to do is we are going to go up here. So we're going to remove moving quad reg from the source list. So we're not building these as part of this test anymore. We don't need the source files here. So next thing we're going to do is call add subdirectories. So add subdirectory quad reg. We can also, so now we have that. We can remove this because it's not needed anymore. And the last thing that we can do is add target link libraries here. Test regression, moving quad reg. So, all right, so little review. What type of target is test regression here? Anyone know? So we created it using add executable. So it's an executable target. Yeah, Jay, exactly, executable. So now we have our executable target being created here by test regression. And then we are linking moving quad reg to test regression. So the code is now split up into two libraries, but we're linking the libraries together again. So it should be the same as having the code be in a single executable. So now we are going to run this code. So we're going to run this code with CMake ... and then make. You can see we built libmovingquadreg.a, and then that got linked into test regression. And it linked successfully, so we set up all of our libraries correctly. Let's see. How about go ahead and raise your hand if it's working for you, and let me know if it's not working. You can also do /test regression. Just sanity check, see it runs properly. All right, 3 people have it working. All right. Seems like it's working for most people, right? Okay, cool. So that's enough. That's enough for part 1. So we talked about targets and we talked about properties. Any questions on targets or properties? This is your chance.
So why do we have two targets exactly? Is one for the test suite and the other's just a library? Or like,
Exactly.
what's the reason? Okay.
So yeah, this target, then here represents the library itself. It's a small library. It's only got 2 source files, but we don't judge these libraries. So this library has moving quadrant and nothing else. So conceptually, this is kind of like its own thing. Like if we wanted to add something else that also used moving quadrant, we could just link that library in. And thanks to the interface include directories that we set up, it'll automatically include the right folder. We won't have to mess around with that.
Okay.
So what we did was we separated out the library and its test suite. All right, now we're going to go back to presentation and talk about build types and compile flags. Now, these are things that you might need to work these a little less because you kind of just need to set it up once for a project, but it's also a very common stumbling block for newer people on CMake. I know this confused the heck out of me when I was new, and sometimes it still confuses the heck out of me, I'll be honest. So let's talk about the weirdness that is cache variables. So like all build systems, CMake provides a way for you to pass command line options that affect the build system's behavior. But it's also important to have a way to store the results of different tests, like testing things on your system, so that the CMake script will run a lot faster when you run it subsequent times. Because sometimes it can take like 30 seconds plus for it to do all the tests that it needs to build a piece of code. You don't want to have to do all that again. So for CMake, both of these things are achieved through a mechanism called cache variables. What cache variables are special variables that keep their values between invocations of CMake. So you can create a cache variable using an alternate signature for set. So what this is set variable value. Value can be a list or whatever, but then after the value you have cache, then the type, which is one of bool, file path, string, or internal. You can check the docs to see what exactly these mean. And a documentation string, which is used to be like to store it in the database to say what the cache entry is. And finally, force. So this function is intended to create an option. So the weird thing about it is if you call the first time you call set cache, right, it'll create a cache variable. If you call set cache again, then it won't overwrite a cache variable that already exists. If that cache variable already exists, set cache will do nothing. However, if you give it force, then it will overwrite the cache variable with its current value. This is kind of a side effect of it being used for 2 different things, to create a command line option and also to store internal data. Like it needs 2 different behaviors, one where it always stores the data and one where it just stores the default, but then you can update it as the user. Kind of weird, right? It's pretty weird, but it's what we have to work with. So cache variables can be set on the command line using the -d option. So be like -d my cache var equals some value. So the idea is you can use set cache to initialize an option, and then the user can override it on the command line. So but if your script just needs to store data and doesn't need to make it an option, use cache internal and then use force to update the data in the cache. So if you want to, so one of the kind of better kept secrets of CMake is that if you really want to get an idea of what a build system is doing, you should view the cache variables, because they're kind of like somewhat meant to be user editable, but then sometimes they're also not. It kind of depends on who wrote the build system and what variables they used. So there's 3 ways that you can edit the cache variables. The first way is by directly opening the file CMake cache.txt that's created in your build folder, or you can use the ccmake tool, or you can use CMake GUI. So both of these are ways that the CMake people made that can configure CMake projects in a more user-friendly way. The idea being to kind of show each cache variable as options. However, the problem is that 95% of users don't know these tools exist, so the developers don't bother actually making the interface any good for a build system. So it always gets cluttered up with junk that users will never actually want to change in the CMake cache. So, and then because it's cluttered up with junk, nobody ever actually uses these tools. So it's kind of a bit of a chicken and egg problem. I don't know if there's an easy solution other than developers just trying to put some effort into cleaning up their CMake cache. Like you can actually look at the cache for the thing we've been working on. If you open up CMake cache.txt, make that bigger. Here we go. So these are all the cache entries that created. You can see these are all the internal ones that CMake is using for its own like data storage and bookkeeping. And then you can also see that all of these cache variables are sort of the user editable ones, at least theoretically. Like the compiler path, the compile flags, that kind of thing. We'll be talking about those in a bit. So here's an example of how you would actually set some cache variables in code. So in this case, the code sets my bool var, my path var, my internal var. We can see that in the cache file, these are generated in these ways. Make sense? All right, so then so if we view those in ccmake, which is short for curses CMake, curses being a library for displaying things in the terminal, we can actually see the more user-friendly representation of that. And notice that it's hiding a lot of those CMake internal variables here as well. So we can see how these get set up. My bool var, my path var, and my internal var. We can't see the internal var. We can see my bool var and my path var.
What exactly is internal?
Internal is basically means like the cache is just a flag to CMake that means the cache variable is used for like internal bookkeeping and isn't intended as an option. So it means it will be hidden from things like this. It doesn't have any other effect on how the variable behaves. It's kind of just like a marker to like not display it in the user settable area.
So internal types, like when you specify internal, does it not have another type like a bool?
No, it doesn't have another type. Remember, CMake variables don't actually have types. They're just strings. The only point of this type is basically to know what type of like text box to give in the GUI here. You can see like my bool var has a checkbox, my path var has like a folder selector or a text box. I think everything boils down to a string, but
Okay.
the type is used to know how to display it in the GUI, basically. That's the only function of that. And internal things aren't displayed at all. You can see like the doc string here, path to my thing, turned into the tooltip here. But again, most people don't use this or know it exists, which is kind of sad because it's actually a very cool tool, especially if you have a complicated project with a lot of options that you need to set. And you don't want to spend ages going through the text file. So it's worth giving CMake GUI a try if you want to try it out. So next thing we're going to talk about is cache variable overriding. So this is one of the most confusing rules about CMake. Even I still mess this up all the time. So the rules are that depending on what type of variable is already defined, set commands can have different weird effects. So of course, if a local variable is defined and you set another local variable, then the local variable's value is changed. That's pretty straightforward. If a cache variable is already defined and you set a cache variable without force, then it doesn't change the cache variable. It just leaves it as it is. If a cache variable is defined and you set a cache variable with force, then it'll overwrite the value of the cache variable. If a cache variable is defined, you set a local variable, then it will shadow the cache variable for as long as the local variable is in scope. So the cache variable is still there, but it's hidden by the local variable. But now here's where it's really weird. If we have a local variable and we set a cache variable with the same name, if the cache variable was already in the cache, then it stays out of scope. But if the cache variable didn't exist yet, then it deletes the local variable and the new cache variable goes into scope. It's the weirdest thing I've ever seen. I don't know who came up with these rules. I really want an explanation. But these are very complicated to remember, and it's caused a nasty bug or two in my code, not remembering the specific rule. It's unlikely that you'll run into it, especially if you follow the recommendations I'm going to give here about how to set compile flag variables, but it's good, something to be aware of. This is weird behavior. The shadowing thing is probably a more common thing to see. I always put a comment that says like, this shadows the cache variable with a local variable, so people don't get confused, because it can be pretty confusing.
Hey, Jamie, did you see the question?
Yeah. Why does the hamster cross compiler fail in the first invocation, only works on the second? That is exactly due to this last issue, where it has different behavior the first time you run CMake when the cache variable doesn't exist, because it will delete the local variable that contained the correct thing, and then the cache variable containing the incorrect thing would be created. Then the second time you run CMake, the cache variable already exists, so the local variable that contains the correct thing stays there and everything works. That was the bug we had to fix a while ago, but it should be fixed now. We changed how we do compile flags.
But
Well,
why
this
would you
is
ever
not compile flags. This is one thing that I've been running into in the build system I'm making for relativity. It's like the generator isn't set the first time you run it, and the second time, I guess somehow when you set it on the command line, right, with the -G flag, then the second time it already has it and it can continue. But the first time the generator isn't set, so then it just fails.
What do you mean the generator isn't set?
I don't know. It just errors out and says there was no generator set.
Huh, that's pretty interesting. I've never seen that before. You'll have to send me that error. I'll take a look at it after.
Okay.
Sounds like something pretty creative has happened.
All
right.
Jamie, why would you keep two of the same? Like, if you had a cache variable, why would you make another variable with the same name as a local variable?
Well, a pretty common reason actually would be like if you want to append something to the cache variable, but then don't store it in the cache. But you're right. Sometimes there might not be a good reason for it. Sometimes it can just be like a preference thing. Like I think one common reason would be like you want to append something to the cache variable, but then not store the appended version back in the cache. Just have something that's a locally extended version of that cache variable.
Okay.
But yeah, you could probably go a long time without setting that if you want to. It's not required. All right, so here's our first cache variable practice. What will this code print? Remind you of Intro CS classes yet? Anyone got a guess?
It's going to print the first thing, right? Like /user.
Exactly. So in this case, the first cache sets the cache variable. Then this cache variable doesn't set the cache variable anymore. Or it doesn't set it because it already exists. So that will print stuff we installed /user. Now this one, what will this one print? /opt, exactly. So in this case, the first cache variable call will set it to /user, but the second one will set it back to /opt. Because it has the force flag, it will overwrite the first cache variable. All right, now this one. /user, is that your final answer, Jay? All right. Not exactly, because so this is back what I said, that local variable deleting nonsense. So the first time CMake is run, there's no cache entry called install location. So when the second line runs, it will delete this local variable and replace it with this cache variable. So it will print /opt. Then the second time CMake is run, the install location cache variable exists. So this set will shadow that variable, and the second one will do nothing. It's very weird. Right? This is crazily weird. But okay, enough about cache variables. We've wasted enough of our life on this. Hopefully this will explain it so you won't run into more trouble later. Gadhian?
So when you run it the second time, and then when you set the cache string again, does it not do anything?
Yeah, that's back to this fourth category here, where if there's a local variable set and you set a cache variable, it does something different depending on what cache variable already existed.
Okay.
This is kind of
confusing.
Yeah, I know. This was kind of a mean case. You're unlikely to run into this, but if you do run into it, it's good to know what the heck's going on. So next we're going to talk about is build configurations. So build configurations are what CMake lets you use to adapt your build for different situations. Most build systems have the concept of debug and release configurations. In the debug configuration, optimization is turned down to either a really low level or disabled, like I talked about -OG and -O0 last time. So, and then debug information is generated in release configuration. So the point of that debug configuration is you can debug code, but it makes your programs run way slower and take up a lot more disk space because debug information is thick. I've seen a program that was like 2 megabytes, but if you enabled debug information, it was like 100 megabytes. It's huge. So in release configuration, you have optimization at full and debug information turned off. Sometimes you also see a variant called rel with deb info, where it's release configuration, but there is debugging. So you have some ability to debug it, but it's not as good as the debug configuration. It's kind of a compromise. I like rel with deb info. It's a nice compromise. I wish it had a better name though. Rel with deb info is just not catchy. So, and with CMake, these configurations are set through the CMake build type cache variable. So, this variable controls what your current build configuration is. So CMake build type is often set. You often set it on the command line when you're building, e.g. -d CMake build type equals release. You can also set it through the menu. Like this is an example from CLine when you can change the the build configuration. The main purpose of CMake build type is to control which compile flags are used in your thing. And something we'll talk about later, you can use a thing called generator expressions to make CMake build type control other things. So you can have other things that change depending on whether it's debug or release. Like you might be able to use a different version of a system library, debug versus release mode, or do all sorts of other fun things. So, and CMake build type is one of the many, many things that contributes to CMake compile flags, or the CMake compile flags. This slide shows you every place that compile flags might come from for a given target. Can get a little overwhelming sometimes, but so we've already talked about these properties over here, right? Everyone understand how compile flags come from these properties? Any questions? No questions? All right. So and we also have our compile flags. So there are two global variables, CMake CXX flags and CMake CXX flags debug, for example, that also are a place where compile flags come from. We haven't talked about these yet because they're cache variables, but now we can talk about them because you guys know cache variables, right? So the global compile flags are read from the cache variable called CMake language flags, where language would be like C, CXX, Fortran, CUDA, C#, all the languages that CMake supports. It's that the variable is named based on that. Now, this variable is considered old in that there's a newer and better way available, i.e. directory properties, but it's not legacy because it's so baked into CMake that there's no way they're ever going to change it. So this variable will be around for a long time. One of the reasons it's considered old is that it's space separated, not a semicolon separated list. So working with it can be a little awkward sometimes. However, it's vital for one specific situation. It's the only compile flag variable that's used in compile tests. So like when CMake tests your compiler itself. So if you have flags that are required to make your compiler work, like for ARM, you need to pass like -m CPU to set what architecture you're generating for, you need to put those flags in CMake language flags. Otherwise, it won't pick them up when it's doing the test, and it will say like, hey, your compiler doesn't work. So you have to be very careful about this variable is very important for specific things. Unfortunately, it's also the variable that users have been conditioned to set when they want to add extra compile flags to a project. But you can see how this might be bad because then they blow away the compile flags that the project sets for itself. This is kind of a weird situation that we're in here. So you basically have two options for dealing with CMake language flags. Option one is to ignore it completely. So instead, you want to apply all flags to the directory and target properties. So that would be like add compile flags, which sets a directory property, target compile flags, or setting the properties directly. So this is nice because then users can use these variables to add flags, sort of like they could with like Makefiles or automake by setting like C flags equals. And but that way it won't cause any problems. However, your other option is to initialize it to something useful. What you do that by setting CMake language flags init before the project call. You need to make sure it's set before the project call because it's used as part of the compiler testing that happens during the project call. So you set that there. So the value will then be copied from the init variable when your project is configured. And you need this if, as I said, if you need specific flags to make your compiler work, you need CMake language flags to be set properly. However, you have to make sure users know to not change this to something else, because otherwise they wreck all your compile flags and break your project. This is something we're dealing with on Embed CMake right now. It's a bit of an issue. So the other place that compile flags come from is the build type compile flag. So this is a variable called CMake language flags configuration, or like as with those filled in, it'd be like CMake C flags debug, CMake C flags release, CMake CXX flags rel with deb info, yada yada yada. There's a lot of different configurations. So these are already initialized for you to sensible defaults by CMake. Like for GCC, the release flags are set to -03-DN debug. However, you don't really have to worry about that too much. So because it'll initialize them to defaults. However, you can also set your own value for this variable after the project command if you want to change these defaults. I don't recommend using the init variables for this because it does something weird, which I'll explain if someone wants to know. But best to just set them after the project command and ignore the cache variables. This is a case where it's useful to override the cache variable with your own thing. Makes it a lot easier to work with. All right, so exercise 2. We're gonna get into our next exercise. This is our last thing. Then we're almost close to calling it a day for today. So this is going to talk about how to add some compile flags. We're also going to add some multiple configuration types to this build system. So now let's go back to our text editor and let's open up our code right here. So the first thing we're going to do is initialize the build type. So this is code that is actually provided by, this is what Kitware itself says to use to initialize this, because it's a bit weird. When CMake starts up, CMake build type is initialized to an empty string. So we have to detect the place where it's an empty string and then set it with force to be not an empty string. That's the strange part. Also, yes, this is the easiest way to test if something is an empty string. These quotes are important because if they don't exist, then it will give a syntax error if you evaluate a variable that evaluates to an empty string. Fun times. Not really, not fun times. This has actually caused a lot of bugs and stuff I've made where it's like, whoops, evaluated a variable as an empty string that wasn't wrapped in quotes, so syntax error. Very annoying. I wish they would fix that. Enough yammering. Let's get on with typing. Build type. I'm not going to retype that entire documentation string. Oh, man. This is just the comment on it. It's not really important. There we go. So now we took this and we added that in here. So that what this will do is it will initialize the build type to be release if it hasn't been set yet. So note that this doesn't work for there's some CMake backends like Visual Studio, or rather CMake generators as we call it, that support multiple configurations at a time. I'm not going to go into those here yet because it's a little bit advanced, but no, this code won't work if you intend to support Visual Studio. I put a link in the PowerPoint to a thread that has code that will work, which is a bit too complicated to talk about here. But it's doable. Just know that this code doesn't work for that case. So now we're going to change up our compile options a little bit. So we're going to set the directory property at the top level to add compile options. That sets property compile options at the top level directory. So we're going to add those in right there. So we're also going to take that, before we had --std equals cx ++11, right? We're going to actually replace that with setting the CMake CXX standard variable. This is a built-in thing in CMake. It'll translate this variable to the appropriate standard flag for your compiler. Note that that's something you always have to be careful of, because if you want your thing to support different compilers like ARM-CC versus IAR versus GCC for ARM targets, those compilers all have completely different flags to do different things. So you have to make your build script smart enough to detect what compiler and what version of it is being used and apply the correct flags. There's also a way you can test whether a flag works for your specific compiler. It's quite cool and quite well done. So I will talk about that in session 4. So we will get to it at some point. It's a bit more advanced, though. So we're going to add that. Now we're setting the CXX standard, and now we're adding some compile options to enable standard warnings. Next thing we're going to do is add some build type compile flags. So these are just some defaults. If we put, so our debug flag is going to be -G2-O0. So -G2 enables debugging, and -O0 turns off optimization. -O2 turns on optimization, and -DN debug makes the C assert function not active. Which maybe you don't use that anywhere, but it's kind of a standard thing to add just to disable assertions in release mode. I always think that's kind of stupid because, like, if you run into a thing where you have an assertion, it's still going to break whether or not it's in release mode. But I guess that's kind of standard, at least. You can turn it off using CMake by blanking the CMake CXX flag's release, then assertions will fire all the time. By by overriding this with something that doesn't have -DN debug. Okay, I'm probably talking too much about this, but that's what that's doing at any rate. So we're going to go to here. There we go. So that's in there. So now, last thing we're going to do is print out our new compile flags. Because if we have multiple configurations floating around, how are our poor users going to know what the correct compile flags are? So we're going to put a little simple build report in that shows the current build type compile flags. But how are we going to get those compile flags? Well, to do that, we're going to be a little creative with our variable evaluation. So what we're going to do is go to the bottom of here, and we're going to type up. Oh, sorry, Jay, I just noticed your thing. I thought the str equal operator will check the left and right arguments, and if there's a variable with the same name, it evaluates as a variable. Otherwise, it will see the text as a literal. Yeah, you're right about that. I think I'm just old school, and I like to do it that way. I think you can potentially. So CMake has a weird thing where it sometimes will automatically evaluate variables that are used in an if statement. So like you can use this, and if CMake build type is a variable, that it knows that, then it will evaluate that and replace it with the evaluated version. However, there can be some weird corner cases where if it's not a defined variable, it'll see it as a string literal, and then it won't do the thing that it won't do what you expect. It'll just see it as a string literal. So I'm just paranoid. I like to always evaluate my variables before they're used in if statements if there's any possibility they might not be defined. Otherwise, it might do weird stuff. I'm just paranoid. All right, back to the task at hand. So first of all, so in order to we have to make sure we have to get the uppercase version of the build type, because annoyingly, some places it's like capital first letter capitalized. Some places we need it uppercase. So we're going to make that version using CMake's built-in string to upper command. See, this is another kind of case of defensive programming where it might be empty string, so I have to quote it. And then CMake build type uCase is the variable to store the result in. So now we're going to do message status. You can format this however you want to. Like we could change this to C++. Is we'll print the current build type. Then backslash is a line continue. I always like having text wrap enabled in my editor, but in case you don't, you can use backslash to do this. So CMake, so we want to set one of these, right? But to know which one, we need to evaluate the other variable we created, which is CMake build type uCase. Remember, this will evaluate to release or debug in all caps. So then that will get put into the second variable evaluation. This is CMake's nested variable evaluation. So the thing being evaluated as a variable can itself contain variable evaluations. Remember, it's all strings. So this gets evaluated first, then the string result of this evaluation gets used in this evaluation. There we are. So now that is our build report complete. You guys ready to test it out? Let's test it out. So I'm gonna go here, and what we're gonna do is run CMake ... and we're gonna see what that prints out. You can see that CMake C++ compile flags for release -02-D and debug. So these are the exact ones that we set out. Now we can change the build type with CMake -D CMake build type equals release or debug. Now we see that the new compile flags are used. Like magic. Cool, right? Everyone understand what we did? Working for everyone? Is it not working for anyone? All right, so either it's working or you guys are silent. That's all right. So that is pretty much everything that we have for today. So we talked about targets. We talked about properties on targets, global, directory, and source files. We talked about linking and interface properties, which are propagated by linking. We talked about cache variables. We talked about the build type, and we talked about the global compile flag variables. In my opinion, this should give you enough groundwork to start making basic CMake projects on your own, especially for like embedded devices or smaller projects where you don't have a lot of dependencies outside your project. However, there are still a number of advanced concepts left, especially for desktop build systems that need to find dependencies, handle versions, all that jazz. So next time, we'll start going into this. The first and foremost thing we're going to talk about is shared libraries, the enemy of many programmers, but the friend of the build system program. See you guys next time.